Okay, we're recording. So last time, here's where we were. We were talking about change of variables. I introduced this as a sort of a variation of the substitution rule. So I'm going to start off by reminding you what the substitution rule says. That's easy to write down. Here it is. And again, you might more likely have seen it as a method or a here's how you do them. But I want to think of this as a mathematical statement, and this is how you'd write it, as a mathematical statement. So I want to give you a point of view on why the substitution rule is true. And let me be clear, what I'm about to show you, this is not really even the most efficient way to justify the substitution rule. But it is the way to justify the substitution rule that most naturally allows for extending it into the multivariable context, which is what we're here for. Right? So reminder, I want to think of this as that we actually have a function with a domain and a target, and that's what this g is that's participating in the equation. So that when we write, x equals g of t, right, we're thinking of that as a function where there's a domain on the left and a target on the right. Okay. The two big ideas that go into this point of view on the substitution rule are first the idea of a pullback. And we talked about this a little bit last time. I want to repeat that for the sake of continuity here. So the idea of a pullback, it's just an observation that even though functions kind of go that way, right, they take points from the domain and send them over to the target. Right, so with the function going to the right, points go to the right, but expressions kind of go backwards. Expressions, we say, pull back. And the idea is, here's an expression, right? F of x, we got some expression there involving x, and what happens if I plug in? Well, if I plug in this expression that's written in terms of x, right? If I plug in x equals g of t, then f of x turns into f of g of t. It turns into an expression of t, right? So points push forward, you might say. Expressions pull back. They go the other way. That's just how plugging in works. It's ultimately not that deep of a point. Y'all have been plugging in expressions into other algebraic expressions for a long time, and I'm just making the observation that, expressions go the other way. Okay, so that's one of the big ideas that we're going to be doing here, and you'll notice that, so the idea is, we've got some integral here, and I want to figure out how to rewrite all of this stuff so that it makes sense over here in the t context. Okay, so the next thing we want to talk about is how do I rewrite dx? Right, how am I going to rewrite that thing? Now, there's an algebraic point of view on this, which is that, dx is equal to g prime of t dt, and we'll just view it algebraically. And you can view it that way. There's quibbles that I would make, but I want to take a point of view that fits with this picture. The point of view that fits with this picture is that dx represents a change in the output values. Right? The output value was there, and then a little bit later is here. And I want to think of that dx as representing that change. Well, change over what piece of time? Well, it represents change over time dt. Now, keep in mind that this function, this g function, some arbitrary function. It's not linear, it's not flat, it's some wiggly, wambly, weird function. So this value of t here, t, let's see here, let me highlight. T goes to x. Where does t plus dt go? Well, it's going to go a little further down, but it's not by the same amount, and who knows? It depends on g, it depends on this function. Right? So that's going to go to some other point here, and therefore in this amount of time dt, x changes by this amount dx. Right? So the twist I want to put on this is how do we think about what is going on there? Yes, it's a change in t that turns into a different change in x. But I want to think of it as that we have a subinterval here, a little piece of length, right? And I want to think of that piece of length as being picked up by the function and being kind of dropped down over here in the x axis. But in the process, notice it's bigger, perhaps, maybe smaller. Maybe by some weird coincidence, exactly the same. Probably not, but it's a different size. And that different size, I want to sort of imagine that as being what I'm going to call here the stretching factor. The stretching factor is the amount by which pieces of the t-axis are stretched out in becoming pieces of the x-axis, stretched out by the function g. So, of course, we all remember our calculus, our single variable calculus, and we also remember just broad strokes that derivatives are what turn input changes into output changes. So we know that stretching factor is g prime. Yeah. But I want to think of it as such, and think of it as that's part of the process here. So those are really the two big steps that turn this integral on the x-axis. I pull back to get an integral on the t-axis. The integrand changes, partly because of plugging in, partly because of the stretching factor. Right? The bounds change because, well, of course, look at the values of t are not the same as the values of x. The values of x are g of those values of t. So the bounds change as well. And there we go. We have a result, and this is, of course, the integral form of the substitution rule. Alrighty. So the purpose of this discussion. I'm sorry, you had a hand.
I'm still kind of having trouble understanding the whole that language. So what is the integral on the left, and right? What are they?
Yeah. So I'm imagining that I'm starting off with I've got this integral on the right, and I'm going to try to rewrite everything here in terms of t. Right, that's all, and so everything on the right is a statement in the language of x, and I want to translate into the language of t. That's cool? Okay. So again, why did we have this discussion? It's not because I want to solidify single variable calculus for y'all. It's that I want to establish a point of view that we can then extend into the multivariable context, and that's what we're ready for now. So we can imagine some function g that takes not just one input but two inputs and gives two outputs. And so what I have here is x comma y are g of u and v, u comma v. And I can kind of play the same, morally equivalent process. I mean, this, whatever domain I might have over here on the left, I can take all these points one at a time, plug them into G, a bunch of points come out, all together. This whole domain turns into a different, really different, right? It depends on the function G, but really different set of points over here. And I can talk about an expression in terms of x's and y's. And how would I rewrite all of that in terms of u's and v's? In particular, I would imagine an expression that being an integral on this domain. And how would I pull this integral, pull it back through the function, rewriting all of it in terms of u's and v's? And it's the same big picture. Same big picture strategy. X comma y is g of u comma v. We just plug that right in. Plugging in pulls back, right? Then there's also the matter of the stretching factor, by which I mean, and this is a little bit of a nastier bit, and I'm going to have to sweep some stuff under the rug here. But if I look at a little piece of the UV plane, a little piece of area, du dv, and I ask, is that the same as a piece of area over here in the xy plane? Its image, if I take these points and literally plug them in, look at the image of this little subrectangle. Is that area in yellow the same as that in green? And well, of course not. It's all stretched out and stuff. And exactly how much is it stretched out is some details that we're going to work out later. I'm going to just assert that there is a stretching factor. And that factor, I wanted to change the colors. That stretching factor is something that can be computed. And I'm going to show you the formula momentarily. And again, I'm not going to justify it now, but I'm going to claim that if you know this function g, you can write down an expression for how much it's stretching out areas. Details to follow. For the moment, I'm just going to assert what that stretching factor is. Here's the magic formula. It's very easy to compute, as it turns out. The stretching factor is the absolute value of the determinant of the derivative matrix of your function g. Very important formula to remember. So you want to make sure to remember that. Conveniently, it's an easy formula to remember. Determinant of the derivative. Don't forget to take the absolute values. Okay. Now, to be clear, just as a reminder, the derivative matrix is this matrix right here. Now, that's old news. That's chapter 2 stuff, right? Just the definition of a derivative matrix. And I'm also going to point out, this is just another notational thing. When you take the determinant of the derivative matrix, it's really convenient to rewrite that with this little weird notation right here. This is a made-up notation. Don't think of this as something you can make sense out of existing notations. But partial xy, partial uv. The idea, a motivation, a point of view on the motivation is that I'm taking the variables x and y and looking at their partials with respect to u and v. Notice those are the partials that are here in this derivative matrix, right? Notice also, though, that the way I've got it written as a fraction, and again, it gives me the willies to say that it's not a fraction. Look, you see right here, it's a determinant. It's defined as a determinant. It's not a fraction. But we write it as a fraction for a combination of reasons. One is, fractions are scalars, right? And I don't want the derivative matrix itself. I want the determinant. The determinant of a matrix is a scalar, right? So this notation is consistent anyway with the idea that I need a scalar to represent, again, that stretching factor. The other reason that I'm going to write it like this, as a fraction, is as follows. It's a really nice little, I'm going to call it a memory tool. You'll see examples in a few minutes of why this is useful. But if I think of area in the xy plane as being dx dy, and if I think of areas in the uv plane as being, as I've written here, du dv, and if I write this stretching factor as partial xy, partial uv, if I use that notation, then notice these being equal, it's kind of like these canceled. Now they don't, right? This is not a fraction, but as a memory tool, I think this is satisfying. And again, I'm going to show you another example in a few minutes of how this can be really, really convenient. Right? So I'm a big fan of this notation. I hope you'll use this notation. Just realize that what you're meaning, what you're actually saying when you write this down is you're actually saying absolute value determinant derivative matrix. Okay. All right. So let's do an example and see what this looks like in practice. The rubber meets the road. And by the way, this is a highly manufactured example. I just want to kind of get one under our belts, get one in the win column, and then we'll talk about more sort of, real world in practice. How do we actually do this day in and day out? Some harder questions are going to come up. For the moment, I'm going to suppose that we have a function like this here given. That's pretty, what's the word I'm looking for? Unrepresentative. But again, just to get one under our belts. This function, this is what we call the change of variables function. given. And well, that said, then of course, if I have a domain in the UV plane, I'm going to say the unit square in the UV plane, that I could talk about what its image is. D is the image. It's what comes out when you plug in that unit square into that G function. Now, this is all just set up, and again, this example highly manufactured. Don't worry about the lack of realism here. Okay. So we've got a domain in the UV plane. We've got its image in the target XY plane. We've got the change of variables function that relates them. The question asks us to compute an integral over that image in the XY plane. So we want to compute an integral over here. Oh, whoops. I want to compute an integral over here. How am I going to compute this integral? Now, before we get to the actual solution, let's take a moment to recognize how much we don't want to do this. If this were my domain, if I had to slice this up as an iterated integral, well, I'm going to say the old-fashioned way, if I had to, slice, dx dy or dy dx, whichever way you go, corners, right? Best case scenario, this is going to be 3 integrals. That's no good. Right? I'll also point out we don't actually know the equations of these edges. I don't have them as equations. I have them kind of parameterized or something, right? So knowing how to relate, how would I solve for y as a function of x on this little piece of curve right here? That's another problem that I don't want to have to deal with. So what we're going to do is the pullback concept, right? I'm going to take what I know about this expression on the right. I'm going to rewrite everything and turn it instead into an integral that happens on this domain. And this domain is super. I love this domain. It's a square, right? If I do an iterated integral on this, the bounds are zeros and ones. It's my favorite. It's everyone's favorite domain for a double integral. Right? So, big picture strategy, we're going to take the integral that we've been asked about here, we're going to pull back, and instead compute a different integral over here. All right, is everybody happy with the sort of the context, the big picture? We got some details to work out now. So, there we go. Okay, so we're going to need to know the stretching factor. So let's compute that stretching factor. Stretching factor is this determinant. Well, absolute value. Don't forget your absolute value. For the moment, though, let's just compute the determinant. See what we get. We're going to take x and y. By the way, easy to forget it, but don't forget that's x, right? And that's y. Right, now I emphasized that here. I actually wrote, there it is. There's x, there's y. I explicitly indicated as a reminder. But in practice, keep in mind when you have a change of variables function, those outputs are the output variables. Okay, so there's x and y, and you can take the u partials and the v partials. The u partials go there. The v partials go there. Y'all can check for yourselves. Make sure you can do that. Right? Computing partial derivatives, assembling the derivative matrix, and then you take the determinant, a little bit of algebra, and here you go. And a lot of people will make a mistake and just kind of say, "Okay, there you go, stretching factor, boom, and spike the football and proceed algebra," and that's wrong. Very important little detail. You have to take the absolute value. Now, in this particular case, taking the absolute value is not obvious. Right? How do I take the absolute value of this expression 4uv minus 9? It's not immediately clear. Is that positive or negative? Right? Not obvious. It turns out there is an easy point of view on how to address this in this case. Don't forget where all of this comes from. Don't forget about your picture. Your diagram describes what each of your variables is doing. And in particular, you can see right here in the diagram that u Right? There it is, u. On our integral in question that we're going to be pulling back to, u is always between 0 and 1. Right? And analogously, v, there it is, v is always between 0 and 1. So I can just eyeball this expression as it turns out. 4uv, this thing here is definitely less than 4. 100% always for every point that I'm actually interested in. I don't care what's going on for other values of u and v, just on the domain I'm interested in. 4uv is always less than 4. So when I subtract 9, definitely negative. No doubt. 100% definitely negative. And the absolute value of a negative expression, is the negative of itself. So, that. Now let me pause on that. Is everybody happy? Is everybody comfortable with my claim that, 2 seconds, that when you take the absolute value of a negative expression, the absolute value is the negative of that expression? It sounds weird to say. Okay, yeah, question in the back.
So if it was like, it was negative for part of the interval and then positive, would
yeah, it becomes a hard problem then. It's a great question. Let's suppose that it had been some sort of a weird thing, like there was that over here it's positive and over here it's negative, right? Then we would have to break it into two separate integrals, and it becomes an undesirable. It's a bummer. Yeah. So, since I'm in the process of showing you a manufactured best case, first time out sort of example, I rigged it where that doesn't happen. Yeah. And in practice, you'd be surprised how often it just ends up not being a problem. There are some particular functions that we're going to use as change of variables functions very often. And those functions never have this issue. So it's not going to be that big of a deal most of the time. That's a great question. Yeah. Okie dokie. So we've got our stretching factor and we're in business. Here's the integral that we were asked to compute. Notice the pullback, and I'm going to zoom back out so I can emphasize. You do the pullback by everywhere you see an x. You got to rewrite what x is. Right? And you got to remember to do it. Right? A lot of students make this mistake of thinking, oh, well, I'm rewriting x's and y's in terms of u's and v's, so I'll just erase where I have x's and I'll just put a u there instead. It doesn't make any sense at all. X is not u. X is this thing. Right? So likewise, what is y? Well, according to this, y is that. So there's the sort of the plugging in part of the pullback. Don't forget to plug in your stretching factor. Pardon me. The absolute value of that determinant. Got to put in that stretching factor. And then we have, in effect, we've pulled back the dx dy as stretching factor times du dv, and now we're in business. We literally have now turned our nasty integral on this really ugly domain, we have turned it into an integral that's on the unit square. And this then is an easy integral. And at a glance, now it's tempting to say, oh, but this looks pretty easy to me. No, it's the domain. The domain is what stinks. Right? We were trying to fix the domain. Yeah, sure, our integrand got a little weirder. But it's just a polynomial. Polynomials are in the big picture easy to deal with, right? So slightly less desirable integrand, much more desirable domain. That makes that an easy integral. Yes?
And easy domain just means that our bounds are simpler, right?
Yes, that's right. That's right. Yeah, exactly. And that's the big problem. Of course, I'm sure you noticed when we were doing double integrals and triple integrals that ugly bounds is what makes for ugly computations. Yeah, right. And corners, right? Every time you hit a corner. So there would have been 3 separate pieces here because of the 2 corners we would hit. Here, just the 1 piece. Yeah. Alrighty. Okay, so that's our first example. So Now, what do you use as your change of variables function? This last example we looked at, I manufactured, I gave you the change of variables function as part of the statement of the question. Most of the time, that's not how it works. There are certain functions that are useful fairly often. Here's a couple of them. Translations. If you have a function that is a translation that moves vectors by adding a comma b, if you think about it, pulling back would just translate your domain by the negative of that vector. Okay, there's kind of an undoing. You'll see an example in just a minute. But simple geometric things that you can do. This is what it looks like when you undo, and these steps can be useful to rewrite your domain as something simpler. So let's see an example. Specifically, I'm going to show you an example of this one. Claim that if you have a counterclockwise rotation as your change of variables function, what that will effectively do is rotate your domain clockwise. Clockwise, not counterclockwise. By that same angle. Here we go. So, let's suppose we've got the following domain. It's a square with certain corners at these 4 points, which you can plot without too much trouble. There's your 4 points. The square with those 4 corners is this. That's your domain. And notice again, this is a pretty undesirable domain. I don't want to have to slice this because as I slice, I'm going to hit a corner right there. And then as I continue to slice, I again hit a corner right there. And thankfully that's the last one, but it leaves me with 3 separate integrals. This is a no fun, undesirable domain. We don't want to have to deal with this domain. Is everybody on board? Everybody see why this is bad? Yeah. Okay. So I'm going to view this domain as being a rotation, and as promised, we're going to use a counterclockwise rotation. Right, counterclockwise rotation, and we'll talk about the algebra in a minute, but counterclockwise rotation. You can see that this blue undesirable domain is a counterclockwise rotation of, that yellow square there, which of course now, because it's part of, the input space, I'm going to draw it over here, but you kind of imagine it being sort of over there. So our domain is a counterclockwise rotation of this square. Everybody on board? What happens then? How do I think of that in the pullback? Well, in the process of pulling back, then I'm effectively taking this square and I'm turning it into a domain which is that square. Effectively, by using the counterclockwise rotation, I'm taking my given domain and I'm clockwise rotating it into something that I actually like. So there's that kind of that undoing, sort of like, there's 2 ways to. There's a backwards and a forwards involved in this scenario. Everybody good? Okay. Now I hope you all remember your linear algebra. This is something I mentioned before, long ago, start of the course, that one of the big things we're going to be doing is understanding linear transformations. In particular, geometric linear transformations like rotations, understanding them as being represented by matrices, and understanding how those matrices come out of looking at images of standard basis vectors. So we talked about this on first day of class, in particular to how to find a matrix representing a linear transformation. Specifically, the matrix has columns that are the images of the standard basis vectors. So, if necessary, if you need to, go back to first day of class and remind yourself of how that works. I'm going to take this as a prerequisite given for today in class. If you have questions about it, you can go back to those notes. You can go back, of course, to your linear algebra notes, book, etc. You can come to office hours. Happy to elaborate in office hours, no problem. Help room. The other professor's office hours, a lot of resources. make sure you can do this. Make sure you're good at this linear algebra stuff right here. Okay. All right. The specifics of the points that I'm given here, like, that point right there is that point right there. Little bit of trig and thinking about these coordinates, you can identify that this angle is pi over 6. And so we're rotating by an angle of pi over 6. That allows us to compute the matrix exactly. There's our rotation matrix, and therefore that is our change of variables function. Okay. And to do the pullback, we need to take the stretching factor. So Jacobian determinant of the derivative matrix, various partial derivatives to take, and blah, blah, blah. And that stretching factor is 1. And I will point out that, of course it is. It's a rotation. Rotations don't change areas, right? Rotations don't stretch at all. So, geometrically expected, yes. But on an exam, do keep in mind, when I put a question on the exam, it's because I want you to demonstrate your proficiency with the methods, right? And so I do want to see the calculation, even if what you're doing is geometrically obvious. Even the calculation. How are we doing so far? We're all ready to do the pullback now. Got everything that we need. And here we go. So, let's see here. I guess I need to have that on the screen too. Okay, here we go. Okay, so 2x minus y. 2x minus y becomes this. Because, don't forget, x is that. Right? X is what the first coordinate of the output from our change of variables function. And then likewise, y, what is y? Well, y is the second coordinate of our change of variables function. So that's just plugging in. In some sense, not much happened there. Don't forget, though, to plug in your stretching factor. Right? Our stretching factor, we've already computed. It's 1. It's the absolute value of 1. And then our integral turns into that. And again, casual glance, if you're too heavily focused on integrands, it's tempting to say, well, I like this integrand a little better. It's the coefficients in this linear polynomial are slightly more attractive than the coefficients in this linear polynomial, right? That's not the point. The big point is they're polynomials. Both of these integrands are fine. The huge, overwhelming point here is that the domain is much nicer. And just as a reminder, put it back up on the screen here. This integral we were given is an integral over the undesirable domain. We have now turned it into an integral over the more desirable domain. So big win, constant bounds, no corners, much easier computation. Everybody happy? Alrighty. A couple of things that I have to say. This has to get said. For this to work, you do need your change of variables function to be continuously differentiable. It just doesn't work otherwise. This is a regularity issue. Again, not really the focus of what this class is about, but you got to say that. It also has to be invertible. It has to be an action that you can undo. And notice rotations are a great example of this, right? If I have something in space and if I rotate it, that's undoable. I can rotate it back. That actually is important in the for the theorem to work. But again, good news. Practically every function that we're going to have any desire to use as a change of variables function is both of these things. Yeah.
So the change of variables function, does that refer to the function that's the integrand of the pullback? Or
The change of variables function is the function there that that's the relationship between the output variables and the input variables. Yeah. So not to be confused with your integrand, right? It's not the same as the integrand. It's the function that relates the new domain, the old domain with the new domain. Okay. Yeah. Great question. Yes.
So in the list of transformations, you say counterclockwise rotation?
Yeah.
Is it like clockwise rotation? Can we do a similar thing?
Yeah, you can use any kind of rotation you want. I'm just the reason I picked counterclockwise here, for one thing, it's just kind of, I don't know, normal, right? It's easy. I don't know, maybe easier, but there's no law on that. But just remember, whichever way your actual change of variables function goes, effectively what that's going to do to your domain is going to be sort of the opposite of that, just because, again, we're pulling back through that function. Yeah. Okay. Alrighty. So, some situations come up, surprisingly often, where instead of, I have a domain and I view it as being an image, and that my more desirable domain, is over here, and that my more desirable domain is kind of the pullback. Sometimes you find yourself going the other way. Sometimes I need the function to go this way. It's just easier to write down the algebra of the function going this way, namely that my new domain is actually the image, not the pre-image. Sometimes your function's backwards, is the point. And I'm going to show you an example of that in just a minute, but first I want to give us the tools to properly deal with it. Quick observation to make is that whatever domain you have over here, whatever its image looks like, if you compute the stretching factor for the function that goes forward, well, look, there it is. And if you compute the stretching factor for the function that goes the other way, stretching factor, well, there it is. Now let's take a moment on this, though. Why is the stretching factor this? For this orange function, the output variables are u and v. So output variables, partial uv, with respect to the input variables. Well, again, the input variables to this orange function, the input variables are x and y. So the stretching factor for the orange function is partial uv, partial xy. And the clever observation is to note that when you do both of those together, right, well, your green domain over here, goes over there and then comes right back to where it had been. Right? If you have values of u and v, and you convert to x and y and then convert back to u and v, you get right back to where you had. Nothing happened. Right? So altogether, the composition, the stretching factor is 1 because nothing happened. Right? And so what we get out of that is this identity down here. We get this identity that these two stretching factors are multiplicative inverses of each other, and in other words, writing them like fractions, this is another example of how that's actually kind of convenient. We know they're not fractions, they're determinants, not fractions, but this is yet another way in which they kind of behave like fractions. And so, yet another reason why I really like this notation. Okay. All right, so let's keep that in mind, and here's my next example. By the way, this is going to look like a manufactured, made-up, irrelevant, non-real-world example. It's not. Just FYI, where I got this example from, anyway, this is a variation, to be fair. But back in my undergraduate days, I was taking a thermodynamics class, and you have to study something called a Carnot engine, or a Carnot cycle. And if any of y'all are engineers, you'll probably eventually take a thermo class, and you'll study the Carnot engine. And involved in that calculation, involved in that subject, there's a calculation where you need to compute an integral over a domain that really looks almost exactly like this. It's a very weird domain, but it comes up very naturally in that context, and it's bounded by a sort of related pair of curves where x, y are constants, and then another related pair of curves. Where x times y to a power are constants. This is almost lifted straight out of my thermodynamics textbook from way back when. The exponent I'm using is 2 in the actual example. It's not 2. It's a weirder number, but for the purposes of what we're doing, this will be more convenient and just as representative. We don't need to get bogged down in annoying numbers. Okay. All right. So we have this domain here, and suppose you want to do an integral on this weirdo domain. How am I going to compute that integral? Okay, so what I'm going to do is I'm going to relate it to, as you might have guessed, a much more desirable domain over here. The way to do that, this is a trick. I never would have thought of this myself, I'm pretty sure, but somebody showed me. And now I can do it because they showed me. Now I'm going to show you that you can do it. Again, don't think of this as, would I have thought of this on my own? Think of this as, oh, I'm glad someone showed me this. Okay. So the trick is, when you have this scenario that your domain is defined, now there's some very tricky points here, by certain functions being constant. Right, I got xy equals constant, and then I've got xy squared equals constants. Said differently, if your domain is defined by various level sets of 2 functions, level sets, keep in mind, where those functions are constants, right? Then let those functions be your change of variables function. And let's just think about what just happened there. And I'm just making this arbitrary choice again. Ask you to trust me on this for just a moment. If I make these my function, then for one thing, the function does, as predicted, go the wrong way. Right now, I've got u and v as functions of x and y. I am not going to be viewing r as being an image of my change of variables function. It just isn't. Right. But something really nice happens, and that is that, keep in mind, if I say xy is a constant, and if I then further say that xy is u, then that curve becomes u as a constant. And that's a straight line. So that's the big idea. Take whatever algebra that you're given, however it comes to you, if you want to use this trick, that is. Rewrite your algebra as level sets. Got to be level. You got to have stuff equals constant. Level sets of a pair of functions. Those functions then become your change of variables. We'll talk about how to deal with it going the wrong way, and then those domain defining curves become straight lines. And then, of course, the other curves are where xy squared equals various constants. That means v equals various constants. We get straight lines going the other way. Question?
So how do we know whether to take xy equals u or xy equals v?
That's a great question. It doesn't matter.
Okay.
Yeah, which one you call u and which one you call v, it's going to work out in the wash. It doesn't make any difference at all. The only difference it'll make is that if you switch them, then when you compute your stretching factor, that switch will introduce a minus sign. But that minus sign is going to go away when you take the absolute values. So it really doesn't matter. Great question. Yeah. Anybody else? Okay, so that's the neat trick. Now everything kind of works out. A couple of detail devils to worry about. But let's compute our stretching factor. Let me erase my mess here. There we go. So the stretching factor. Now, I can't, at this point, compute the partials of x and y because I don't know x and y. So I can't compute partial xy, partial uv. What I can compute is partial uv because I have formulas here for u and v. And I can take their partials with respect to x and y. And thus I've computed partial uv, partial xy. And that's a little algebra, and there you go. What we're going to need is the other. We're going to need partial xy, partial uv. And this is where we cite the result from above. These two things here are reciprocals of each other. And so if this one is xy squared, then this one is 1 over xy squared. And I claim, this is the stretching factor that we need. Why is this the one that we need? Go down to the algebra on the next page. Keep in mind what I've been asked to compute. I've been asked to compute this integral in the xy plane. I want to rewrite that in the uv plane. So I'm going to need whatever stretching factor it is. I'm going to need whatever that thing is that multiplies by du dv to give me dx dy. And so which way do you want it? What do I need to make this work? Well, I need the little fake cancellation to happen, right? And again, that's just a memory tool. There's not actually a fraction. There's no cancellation. But you need it to be in the way that's going to make it cancel, to make it look like it would cancel. So, well, that's why we need partial xy, partial uv. And we have it. So, boom. And then you plug it in, and we get down to this. And now, if this had been a regular change of variables problem, then this would be an easy integral. Look at the bounds, the constants, right? I mean, by design, we rigged it up to where these would be, nice. The other weird thing about these examples, though, is that when your change of variables function goes the wrong way, you can't plug in and pull back the variables because your function's going the wrong way for that. So then you have this issue of, okay, now but I really do have to convert this integrand into u's and v's. This is a uv integral. I need my integrand to be in terms of u's and v's. And how do I do that? And there is no single method for this. This is it's different in every example. Roughly speaking, though, here's what you have. You want to rewrite it in terms of u and v. Don't forget what u and v are. U is this, and v is this. And so I reason here, I speculate, I should say, here as follows. I have a product of powers of x and y. I want to write that in terms of u, which is a product of powers of x and y, and v, which is a product of powers of x and y. So I have a couple of products of powers of x and y, and I want to get a different product of powers of x and y. What would I think that I would do? What do you think you should do to products of powers to get a different product of powers? And I'm thinking that you take a product of powers of the products of powers, then that will continue to give you products of powers, and maybe you can arrange it to be the one that you want. So this is just, based on the form of what I'm looking at, it seems like a reasonable guess. And with this being the case, you can do a little bit of algebra and solve for these A and B. Product of what powers should you take? You do the algebra. There you go. Right, and so this integrand that I had, I've now written in terms of u and v. Okay. Everybody all right? Okay. And we are out of time, so we will draw the line right there. Next time, I'll start off by showing you where the stretching factor formula came from, and we'll proceed. Okay, y'all have a good rest of your Monday. See you later.